Good afternoon, all of you. So, we studied about first law of thermodynamics in the last class. So, in this class, we will be continuing that with application of the first law of thermodynamics. There are a lot of conditions where we can apply our first law of thermodynamics to situations. And today, we will be considering one situation and see what are the changes being observed. So the first law of thermodynamics, which is delta U or change in internal energy, is equal to Q plus W, and Q is the heat exchange and W is the work done. And we discussed two statements of this equation, which was the internal energy of a system is always constant, and one more statement was that the energy can neither be created nor be destroyed. So if that is the case, we can also understand that the total energy of the universe is always constant. Many processes happen in the universe. Many energy conversions are also happening. But there and all, there is no energy is created nor destroyed, just the energy conversions are happening. So hence we can tell the internal energy or the total energy of the total universe is always a constant value. So with that we start our class. So we are going to consider a condition where we can apply the first law of thermodynamics. So the first condition where we are going to apply the first law of thermodynamics is the work. So we are going to consider a pressure volume work and see how the first law applies on it. Work is done on an ideal gas in a cylinder when it is compressed by a constant external pressure, which is P external, in a single step. So this is the experiment we are going to do and find out how first law will apply. So we are considering a cylinder which is containing of gas. So this is a cylinder with a piston, and the piston we can tell it is friction free, or the piston is freely moving. There is no force which binds it to the cylinder. So it is very freely moving. So we are considering some particles of gas inside the cylinder, and we are considering the force or pressure outside the cylinder as pressure external or Px. So this is the pressure of the surrounding, and this is our system. So when the pressure outside is more than the pressure which is created inside due to the particles of gas, obviously compression will occur. So when this is a freely moving piston, we can tell when the pressure is more outside, the inside pressure is less, then compression will occur. But till when the compression will occur? Till the pressure of the inside reaches the equal value of the pressure outside. There the compression will stop because they are equal forces from both the sides. So there it will stop. So when that is possible? That is possible when we compress, the gas particles are coming more and more close with each other. And in the states of matter, we have studied that when the volume is decreasing, the collision of the gas particles to the walls of the container and to the piston will increase. So because of that increase, the pressure created inside the container will increase as the volume is decreasing. So when we compress, the volume is decreasing. So when the volume is decreasing, collision is increasing, and because of that, the pressure inside is slowly increasing as the pressure external increases. So at a point of time, the pressure inside will reach a value which is equal to that of the pressure external. So when both these values becomes equal, the compression will stop. So as we told earlier, in thermodynamics, we are just concerned about only two conditions, the initial condition and the final condition. For any system, we just see those. So initially how the piston was, and finally how it is. So initial pressure, temperature and volume, and finally how it reached. These are the two conditions which we observe in thermodynamics. And now we will see how much it moved, or what is the volume change in between these two, and what is the length change between the piston 1 and piston 2. So this is the area which was covered by the piston, and we will represent the length which covered by the piston as L, and the volume should be delta V. This is the final volume, which is Vf, and this is the initial volume, which is Vi, and the difference between these two, which we are representing by delta V, and the length travelled by the piston is L. So the volume change between these two stages are calculated by the equation length into area. So the length which the piston travelled and the area of cross section of this cylinder. It can be the area of cross section of the piston, or it can be the cross section of this cylinder. So both are the same. Because it is tightly packed, we can tell it can be the area of cross section of cylinder or the piston. And that is equal to the delta V, or the volume change, which is equal to Vf minus Vi. So final volume minus initial volume, that we will get the delta V, and that is equal to length into area of cross section. Now we are going to find out the equation of work. So for that we need to apply some more equations to this. So this is the cylinder which we did our experiment with P external. It travelled, or the piston travelled for a distance of length L. So the equation of pressure is equal to force by area. This is a common equation for pressure. And if pressure is force by area, what is the equation for force? In the equation of work, we need to substitute the value of force, so that we are finding out the value of force. Force will be equal to area into pressure. So if we rearrange it, force is equal to pressure into area. And if that is the case, what is the pressure applied here? Which is P external, as it is compression. The pressure applied here is P external. So into area, which is area of cross section. So hence the equation for force will be force is equal to P external, the applied force, into area of cross section. So that's how we got the equation for force, and this we are substituting in the equation for work. So the equation for work is force into distance. So here we got the equation for force, and the distance for it will be L, the length which is travelled by the piston. So that is the L which we have. So the equation for work will become force into length, and equation for force is P external into A. This we are substituting here, and we get an equation like this, where W is equal to P external into area, which is the equation of force, into the distance, which is length L. So that's how we got equation for work. And from this, what we can write? So we can alter this equation to P external into minus of delta V, because A into L is delta V. So this equation, if we see, L into A is equal to delta V, or change in volume, that we are substituting here. And why we give this minus? Because when we deduce Vf minus Vi, the final volume minus initial volume is greater than the final volume which we have. The initial volume is bigger quantity and final volume is a lesser quantity. And when we subtract a bigger quantity from a smaller quantity, we get a negative value. That is being shown here. So P external into minus of delta V. And this equation we can write like this: minus of Px is equal to delta V. And one more negative value we are giving, because this negative value we are giving for making the value of work to be a positive value. So whenever we try Vf minus Vi in place of compression, we get a negative value here. So we are adding just this one negative value to get the work done as a positive value. So here we have a negative value here. To compensate that, we put a negative value here also. So both of them will become a positive value. Hence, we get work as a positive value. So that's why we put this negative. So from the beginning, we have all these things done, and after that from this we got the equation for volume change as length into area of cross section. So length is the length traveled by the piston and area is the area of cross section what we have, and that we are substituting in the equation of work. So before that we need to get the equation for force, that we get from the equation of pressure. Pressure is equal to force by area. So force is equal to pressure into area, and in that we have pressure external or the external pressure as pressure in this case. So force is equal to pressure external into area of cross section. This equation we are substituting in the equation of work. So work is equal to force into distance, and force we got. Distance is the length travelled by the piston. So hence we can substitute this L to this distance. So hence the equation will become P external into A, which is the equation for force, into L, which is the distance. So this equation we are altering by substituting the value of A into L from this equation to be delta V. So that we are substituting here with a negative charge, which is from this equation. So Vf, as it is a smaller quantity, and Vi, the initial volume, is a bigger quantity in case of compression. So we get a negative value always for delta V in this case. So we substitute that negative value to that. So P external into negative delta V. So this will be equal to negative of P external into delta V, and this negative charge we put to get a positive value for work. So that this negative and this negative together it will become a positive value. Hence just to get a positive value for work we are adding that negative sign. And now we are going to have a situation where the single step of compression is divided into different parts. From here to here, one stretch it was coming. But in this case, we are not doing that. We are doing the compression in a step-by-step procedure. Slowly it will come till here, then it will stop, then till here, then till here. Like this, slowly and slowly it will compress. But in case of multiple steps, or even if it is done in a single step, we have the same results, because we are just considering the initial step and the final step, or initial condition and final condition. So as the internal energy is a constant quantity, we can have it as a single step or a multiple step. Both will be same, as it is a state function. The path does not matter here. So we are continuing the conversion here, and we will see how the graph will go. So as it is compressing a little bit, slowly the pressure increases, the volume will decrease like this. So this is a pressure volume graph where the initial condition is here and the final will be here. The same thing which we have done in the earlier case. So that initial and final is kept, and we are compressing it step by step. Again we will start compressing one more step, then again the volume is decreasing and pressure is increasing. So again we are compressing one more time, hence we get a one more value. So step by step we did compression here, and in each step we marked a point and we marked the values there. So if you see here, this will be equal to the conversion in the single step also, because if it is done in a single step or if it is done in multiple steps, the result will be same because it is a state function. And the equation for work done here is P delta V, right? The minus P delta V was the equation for the work done. But that we are finding out when it was done in a single step. So here what we do is, for this much portion, for the first step we should find out a P delta V. Then again for the second step also we should find a P delta V. And third, fourth, each of them we can find out a P delta V equation in that, or we can find the value for that. for the work done from here to here and the work done from here to here, and if we sum it or if we take the sum of all the work done, we will get the same value which we have done for the single step. So again, if I tell, if we calculate the work done for this much to this much by P delta V and for this much to this much again with the same equation, so that will be equal to the total P delta V which we have calculated for the single step. So as it is a state function, here path does not matter, or how it is done, or whether it is done in one step or whether it is done in 5 steps or infinity number of steps, it doesn't matter. We will get a same value. So we can tell here the P delta V is equal, or the work done is equal to the sum of individual works done in each of the steps. So the total work is equal to the sum of individual works done in each of the step. So hence we can write this equation with a summation sign. So negative sum of P delta V of individual works done in each of the steps. So that is the equation for step by step procedure or step by step work done. So with this we finish our class, and tomorrow we will be studying about the reversible and irreversible processes with continuation to this. So please make notes and read the textbook properly and submit in the group. Thank you.